All right, so this is 8.2, and let's call it A. We'll see if we can do it in less than 2 videos, but we'll find out. Linear programming, graphical methods. All right, this particular section is focusing solely on using your graphing calculator in order to solve the problems here. And this is just kind of the first bit of information here. And it says that in any linear programming problem, which in linear programming you do not have any exponents on any of the variables, except, obviously the assumed one. All right, so that means that when you graph, you get a straight line. And we have what is called a feasible solution, which is one that makes sense. So in a lot of cases, the number or the answer cannot be a negative number because we're looking at a quantity or a dollar amount or a distance or something like that. So therefore, it has to be a positive number. So that means that it's not feasible to get an answer other than a positive number. Okay, there's constraints going on. And the region, like this region right here, is called a feasible region. It means it works. All right, so here are the constraints in our car rental application here that we looked at, or that you can look at the top of the page, talking about having some money to spend on 71 new cars and how much you're going to spend on each one, that kind of thing. And it gives us 2 basic inequality problems that you plug into your graphing calculator. Then you put this one in there, and then you put this one in there. And that gives you 4 different things going on here. Okay, so this first blue line is my x plus y equals 71. My red line is 15x plus 28y equals 1260. Okay, so again, we make these equal, we graph them, and then the part that is less than is what's going to be shaded. Okay, so this is less than, everything under the blue is less than, everything under the red is less than, but we're looking for what is true for both of these. Okay, so this section here is the only thing true for both the blue equation and the red one. Below the blue is this whole thing, but this is not below the red, so we can't count that. We can only count what's below both of them. And below both of them goes into infinity, except we say that x cannot be any smaller than 0, so it can't be over here at all. It has to be greater than. And our y is also greater than or equal to 0, so here and up. So it only includes this area here. If it did not say x is greater than or equal to 0 or y is greater than or equal to 0, then our answers could be in all of this area down here as well. But because of those constraints, we're stuck with what we've got. All right, so that's basically what we're looking at in this section. Plugging numbers in and getting an idea of what our possible solutions are. So if you go to page 601, middle of the page, Solutions to Linear Programming Problems, it gives you the steps that you need to figure out. Step 1, if a linear programming problem has an optimal solution, and when I say optimal solution, I'm basically concerned with the best answer, where I'm going to get the best possible value or answer that I can get, where I'm getting the best deal, I'm making the most money, that kind of thing. And that will always occur at one of the corners of the feasible region. So on that last picture that I had up there, I showed you where the blue was, and the optimal place would be one of the corners. Okay. Number 2, when a feasible region for a linear programming problem is closed and bounded, the objective function has a maximum and a minimum value. Now let me get one up here so we can look at it again. Okay, so let's just look at this picture here before we really look at in detail about what the problem is. All right, so we've got some maximum solutions here. Here's some minimum and there's some maximum. Okay, a feasible region would be this whole region here, our possible or our feasible answers. When it says closed and bounded, it means that it is closed. There's not an opening. It doesn't go on forever. Okay, it stops here. It's basically boxed in. Okay, and it has then a maximum and a minimum value when that's the case. Like this might be the maximum or this might be the minimum or this, depending on what you're looking for. If the objective function has the same optimal value at two corners, and it also has that optimal value at any point on the boundary line segment connecting the two corners. That means if, for example, let's say that this line went right over like this, okay, and these two corners were the maximum values, okay, or the optimal values. It's saying that this line connecting these two, all the points on this line also have optimal values because it has the same optimal value. We went up 5 here, 5 all along here. So the maximum, the optimal, the best choice would be anything along this line here. Okay, so that's what they're saying here. When the feasible, come on, let's get rid of this. When the feasible region is not closed and bounded, the objective function may have a maximum only, a minimum only, or neither. Meaning that this wasn't boxed in. Let's say that it just went here, and we could go as far as we wanted this way or as far as we wanted this way. There wasn't a boundary over here. That means we would only have a maximum. We wouldn't have a minimum because it goes into infinity. Okay? So, for a closed and bounded region, which we have here, we can find the maximum and minimum values of an objective function by evaluating the function at each of the corners. Okay, 1, 2, 3, 4. At each of the corners of the feasible region formed by the graphical solution of the constraint inequalities. So we're just looking for these 4 points here and determining maximum values. All right, so let's look at example 1. This is the graph of example 1. So let's get everything else up here. Okay, so when you take your graphing calculator and you plug in x plus y equals 5, you get the blue line. 2x plus y equals 8, red line, gives us the boundaries here, which are basically these down here. And what are we doing? We're just finding the maximum value and the minimum value of c equals 5x plus 3y. Okay, so because it's bounded by x is greater than 0 and x is greater than y, this whole quadrant here, which is quadrant 1, is one of the feasible regions, or is the feasible region. You know that it's somewhere in here. We haven't specified that it's going to be this little area here in blue. All we know now is it's this because of this and this. All right. We can graph the remaining boundary lines with technology, with your graphing calculator. You graph that, and you graph that. The first 2 inequalities there. And what you do is you set it equal to y so that you can plug your information in here and get the graph. Alright, so the solution set for the system of equalities is bounded by the lines y equals 5 minus x and y equals negative 2x plus 8. Okay, these 2 problems here. And they say equal because we're looking for the line. We're not looking for what's above or below the line like this says. We're looking for the line. That's why the equal sign. The corners of the feasible region occur at the origin, at the x-intercept of one of the 2 boundary lines, okay, either here or here, we haven't figured that out yet, at the y-intercept of one of the 2 boundary lines, here or here, and at the point of intersection of the lines, y equals 5 minus x and y equals negative 2 plus 8. So this point right here is the other boundary. So we know that one boundary is here, one is either here or here, somewhere, we haven't figured that out yet, here or here, and here. Which, I mean, you look at it and you know they're talking here and here because they've already finished it here, but pretend that you don't see this shaded, and you have to figure that out. So there's two y-intercepts points, 0, 5 and 0, 8. And the one that satisfied both inequalities is 0, 5. Okay? This point right here doesn't solve the inequality because it works for negative 2x plus 8. Okay, 7 works for that. Or I'm sorry, 7 works for y here. It makes that a true statement, but it does not make that a true statement. So therefore, what makes both of them a true statement is below this point right here. So that becomes that one. Okay? And we keep going and we find out that my x-intercepts are 4 and 5, crosses at 4 and 5. The one that satisfies both of them is this one, because even though a point right in here might satisfy my x plus y equals 5, or my x plus y is less than or equal to 5, it doesn't satisfy this one. The only one that satisfies both of them is this here. Okay, what we have there bounded. All right, so there are our 1, 2, 3, 4 points there. Okay, B in this particular one says the minimum value, c equals 5x plus 3y, subject to the constraints. So remember, we've got the equation right here, and we have 4 points. Point there, here, here, and here. So actually we have points. The origin, we have 0, 5. We have 3, 2. So again, 4 corners. And we have 4, 0. We put our x and y values in to this problem here and see what we get. And when we get the biggest number, that ends up being our maximum value. Okay, so that happens when we use 3, 2. Okay, so we take 5 times 3 plus 3 times 2. Okay, so we replace 3 and 2 with y, and we get 21. The other ones are 0, 15, 20, and 21. So this one here ends up being the maximum value. Okay, so that means in our story problem, if we had a story problem, that would be the perfect place that we want to be. All the other places are good places and work, but that is the maximum value. Okay, minimum value would be where these numbers up here, where we plug these numbers in, and we get the smallest or the minimum value, and that happens when we put 0, 0 in, because when we put 0 in here and 0 in here, we get 0 for an answer. So there's our minimum. Okay, I'm going to go ahead and shut this off and continue on with 8.2 B as in boy. This is taking quite a bit longer than I thought it would, but anyway, let's keep going.